In this collection of videos, we are going to introduce the direct and limit comparison tests for series. We'll give an explanation of what they are and what they mean. We'll give a step-by-step description of how to apply these tests, and then we'll work some examples. So here's the formal statement of the direct comparison test. In what follows, we're going to assume that we have a little function and a big function, and that's denoted right here in this inequality with the little function always being less than or equal to the big function. And because we're dealing with series and we're kind of thinking about them as a representation of area, we're going to want to assume that these things that we're adding up are positive numbers to correspond properly with area. What the direct comparison test is doing for us is giving a formality to something that we saw before with some pictures. In the first situation, imagine that we're adding up the bigger numbers and we're getting a finite value when we do that. We're getting a convergent series. Then certainly, if I add up the littler values, then I should still be getting a finite value, and therefore this series should also be convergent. In the second situation, we have something of the opposite picture, which is, imagine that I'm adding up the littler values and I'm already going off towards infinity. Then certainly, if I add up bigger values at every step of the way, I need to end up with something that's bigger than this sum, and there's really no way to be bigger than infinity without being infinity yourself. So that's what our direct comparison test is doing. It's relating back to this idea we had with areas, where in both situations, we're assuming we know something about the nice shape. In both cases, the nice shape is the square, but in the first case, the nice case is the bigger area. In this situation, it's the smaller one. Next, I'd like to talk about the steps we need to take to use the direct comparison test. In our examples, we will be given a series and we generally represent the addends of that series by a sub n. If s is the starting point of the summation that we're considering, and we stop at infinity because we're dealing with infinite series, the first thing we're going to need to do is show that our addends are positive on the interval from s to infinity, and that's coming from this requirement in the DCT. No matter what our a sub n ends up being, the L sub n's or the B sub n's, they always need to consist of positive values. The next step is for us to introduce a different series to the problem. Now the addends for this series I've denoted by k sub n for known addends. What we want to do is always assume that the original series we're given with addends a sub n is the messy region from the previous collection of pictures. And the k sub n's that we introduce ourselves are going to represent the square and be the nice figure from the previous slide. We also want these k sub n's to be comparable to the a sub n's in a particular way, and that particular way is that we would generally like the a sub n's and the k sub n's to have the same rate of growth. Now here's where things get a little bit messy. If we want to conclude something about the sum of the a sub n's from the k sub n's, we need to have the right picture from the previous page. If what's known about the sum of the k sub n's is that we get a convergent sum here, then because the k sub n's are representing the square, and what is known is that the sum of the k sub n's is finite, then in order for us to be able to use the DCT, we have to be in this picture. And what that means is, in order to use the DCT, we would have to argue that our a sub n's are less than or equal to our k sub n's. Conversely, if it's known that the sum of the k sub n's diverges, Then the picture that makes sense from over here, if we're going to conclude anything, is that our k sub n's must be here with the infinite area on the inside, so that we must show that the k sub n's are less than or equal to the a sub n's. So note that this is something that's really tricky about the DCT. What we're trying to show in step 3 depends on the behavior of the k sub n's. In one case, we're trying to show that the a sub n's are less than or equal to the k sub n's, and in another case, we need to argue that the k sub n's are less than or equal to the a sub n's. Now remember that the footnotes on the previous slide are trying to warn us about something. When we originally studied these two pictures, there were two cases where we could draw conclusions, and those are the cases that are stated in the direct comparison test. But there were two cases where we could not conclude anything from the pictures that we had, and those cases were when the area of the square here was infinite. We weren't able to conclude anything about the area of the inside shape. And over here on the right, when the area of this square was finite, we were not able to say anything about the area of this larger shape. So what this means is that when we pick our comparable function, there really is only one relationship between our known function and our unknown function, and it is 100% possible that the relationship we're hoping for in order to use the DCT is not the relationship we have. So you need to be careful when you're attempting to use the direct comparison test that you're only asserting inequalities that are true and not just writing down what you want to be true and hoping that that's the case. However, anytime we do an example the first time around, it's nice to see a time when it works. So let's apply the direct comparison test to determine either the convergence or the divergence of the series given here. So according to the steps that we laid out on the previous set of slides, the first thing we need to do is argue why our addends, the 1 over n squared plus 1's, are always positive on the interval from 1 to infinity. This is fairly clear for the function that we're considering. Whenever we square anything, it's a non-negative number, and when we add 1 to it, it's definitely positive. So when I consider a positive number divided by a positive number, I'm always getting a positive number. So we've checked that our addends are always positive. That's the first step. The second step is to come up with our comparable function. And generally, the comparable function is going to take a look at whatever your addends are and replace both numerator and denominator with equivalent functions in terms of rate of growth of the numerator and denominator. Now in this example, our numerator is very simple, so the 1 just remains a 1. When we take a look at the denominator, the 1 is incredibly negligible as n is going off towards infinity, and so the 1 is going to be eliminated when we're picking our known function, and we'll just use n squared in the denominator. So what we truly believe in our heart of hearts is that this series really ought to have exactly the same behavior as this series. Now this series right here is a p-series, and the behavior of our p-series is entirely understood because my p-value is greater than 1 here. My p-value is 2. We're looking at a convergent series here. What this means in terms of our pictures is that our known function, which is the square, is ending up being finite. And if we want the finite area to trap the messy area, we must be hoping that it's the relationship of this picture going on in our situation. So what we would be hoping to establish is that our messy addends are smaller than our nice addends. And so that is what we'll be trying to establish here. In order to show that, let's start with something we feel really confident about, which is that n squared plus 1 is larger than n squared. As we've seen before, when we take reciprocals, this flips the inequality, and we get that 1 over n squared plus 1 is indeed less than 1 over n squared. So here we are. These are the littler terms. These are the bigger terms. What we know is that when we add up the bigger terms, we're getting a finite value, and therefore, by the direct comparison test, we can conclude that this series must be convergent. Now we still have more to go. We need to take a look at the limit comparison test, and we need to see some more examples and see the complexities of the previous theorem. But for now, we're going to take a break, and we're going to look at this adorable picture of our nice function hugging our messier function and giving us a visualization of that direct comparison test.